Okay, so the definition of deadlock is very simple. Okay, each process in the set waiting for an event, but that event can be caused only by another process in the set. Okay, so there is a set of, in this case, our example is very simple. There are two processes, that's it. Okay, it doesn't have to be that way. Okay, maybe A is waiting for B, B is waiting for C, C is waiting for D, and D is waiting for F, and F waiting for A. Okay, so the set could be very crowded, and it would be difficult to actually detect the deadlocks. But that's the definition of the deadlocks. Okay, somebody, Kaufman, in 1971, okay, defined the conditions for a deadlock. Actually, the deadlock can happen uh, only if all of these cases are satisfied. Okay, if if you don't have any of them, okay, then deadlocks cannot happen. Okay, let's look at them. For example, one of them is mutual exclusion. If the resource is either available or assigned to exactly one process, that's called the mutual exclusion. I mean, the resource cannot be shared at the same time. Either you have it or not have it. It's like the printer, right? I mean, either you are using the printer or not using the printer. You cannot share the printer with somebody else. Once you start writing your printout, you have to finish your job. You cannot stop and let somebody else use the printer and come back. No, this doesn't happen. So mutual exclusion has to be there. Question: is memory a mutually exclusive resource? Is CPU a mutually exclusive resource?
Can you come again, sir?
Is memory mutually exclusive resource or CPU mutually exclusive resource? I mean, the definition is there. The resource is either available or assigned to exactly one process.
I don't think they are assigned to exactly one process.
CPU is like that, right? I mean, CPU can be used only by just one process, right?
Oh yeah, but it works in parallel. But okay,
Yeah,
yeah,
but
but
memory is not like that. Memory could be used by many processes. So, for the first condition, maybe CPU can cause deadlocks, but we will see. Hold and wait, okay? A process holding a resource and can ask for more. If your operating system allows this, if your operating system says that, okay, this process is yours and you can ask more, that's the hold and wait. This is easy to satisfy. This could happen. No preemption, okay? The resources cannot be taken away from a process involuntarily. No preemption. So there should not be any preemption. CPU and memory is not. They are all preemptible, right? I mean, if somebody is using a CPU, although it's a mutually exclusive resource, if somebody is using the CPU, you can preempt that process. You can say that, okay, stop using the CPU. I am going to assign it to somebody else. The same with the memory. Okay, so it is very rare that CPU and the memory can cause deadlocks. Both of them are resources, but I wouldn't say that they will cause any deadlocks because they are preemptible. Printer is not preemptible printer because, as I said before, or the scanner. While you are scanning a document, you cannot stop scanning and let somebody use it. Okay, so no preemption has to be there. And the fourth one is the circular wait. Okay, there should be some kind of a somebody is waiting for somebody, that body is waiting for anybody in the loop in a circle. There must be a chain of two or more processes waiting for the next member in the chain. Okay, so chain is a circular chain. Okay, A is waiting for B, B is C, C is D, and D is waiting for A, something like that. Okay, if you definitely know that, this is the case. This can happen, but no circular wait can happen. Then deadlock conditions cannot happen. So these four things, usually people would know these about the deadlocks. And when they ask a question, they ask you about this. What are the conditions for a deadlock? Necessary conditions. Okay, these are the necessary conditions. Take one away, and deadlock will not happen. So as you see, deadlock for a deadlock to happen, many things has to happen. And if you are designing an operating system, maybe you don't have to be very careful about the deadlocks. Why? Because if you if you if you by design eliminate one of these conditions in your operating system, then no deadlock will occur, or it will occur very rarely. Okay, so we are going to see techniques that will satisfy this, and this. Okay, so in a few moments I am going to show you that, and we will continue with the next chapter. I think I showed you this one with the deadlock modeling. How do you model the deadlock resource allocation graph? Okay, so this is a resource, this is a process. That means that A holds the resource R. This one means that B needs to hold resource S. In this case, there are two processes. C holds resource U, D holds resource T, okay, and C needs T and D needs U. So there's a typical deadlock situation. If you detect such a cycle in your graph, if you detect such a circle in your graph, then there is a deadlock. We know that. Okay. An operating system. What can the operating system do? Operating system can continuously form these kind of graphs and try to detect cycles in it. And if there's a cycle, then what would you do? Maybe you would preempt the resource. Maybe you would kill this process. Maybe you would do something else. Okay, so I am not going to talk much about it. Here is an example. These are the things. Okay, A requests R, A, okay, requests R, B requests S, then C requests T, then A request, okay, this is the, then C requests T, then in this case A requests S, right? And then these are all gotten first. A requests S, it cannot get it, so it needs it. B needs T, and then C requests R. In that case, when C requests R, in that case, I have a deadlock. So I mean, all the operating system sees this one. By looking at this 6 lines of requests, it is not easy to see there is a deadlock. You need to come up with this graph and do the cycle detection. And cycle detection is not easy for a general case. Okay, so that's the resource allocation graphs. Okay, and these are some of the things that you can do with the deadlocks. Okay, the first one is the one that most popular operating systems choose to implement. Ignore the problem. Okay, just ignore the problem. Windows, Linux, OS 10 does this. They don't do anything about detecting the deadlocks. Okay, if there's a deadlock, do something about it. No. So what would be the worst thing when the deadlock happens? Okay, if there is a deadlock here, okay, if there is a deadlock here, what would you do? There are 3 processes waiting for each other. There is a deadlock, and after a while, usually the user is bored. The user is very angry that their processes are not running, then they are not making any progress. What would you do in that case? I would restart my application. That's what I do. So if A is my application, I would kill it. As soon as I kill it, B can continue. Once B is done, C will continue. And since I will restart A later, I will start A later. Okay, it will be done later too. So this can happen, but this is already happening many times to me every week. I have to restart one of my processes because something stupid is happening, and it doesn't have to be a deadlock. Okay, and one more application crash is not a problem. So ignoring the deadlock problem is a very good way of dealing with it. Okay. Second one, if you don't want to do this, detect and recover. Okay, you will let the deadlock occur and detect them and take the action, like the resource allocation graphs. Or sometimes you could do dynamic avoidance. Okay, you would never let okay deadlock happen. You always when a process asks you to do something, you will say that no, if I do this, this will cause a deadlock. I am not going to do this. Okay. And the number four is you design your operating system in a way that, okay, one of those conditions of the deadlocks will never happen. Okay, that's the prevention. So easiest, a little bit more difficult. Maybe this is the most difficult one. Okay, I already talked about detection and recovery. Okay, let the deadlock happen and detect it using this graphs, resource allocation graphs. Here I did that. Okay, I formed this graph and I detected the cycle and I said that there is a deadlock. So what am I going to do? Kill this process G and that will solve the problems. Okay, so I will not talk about how to do this detection algorithm or cycle detection algorithm. It's a simple algorithm, but it is a little bit involved. I am not going to talk about it, so I am skipping it. Basically, it's a algorithm that tries to find the cycle. Okay. Then other types of deadlocks. Okay. So far we assume that there is only one resource named U. Like, for example, P is printer, right? If there is one printer in your system, this resource graphs work. Okay, but what happens if you have five printers connected to your five printers, three scanners, etc. to your system? This resource allocation graph will not work in that case, right? Because if one of the processes is using one of the printers, then the other process can use the other printer. So the number of resources become important. Okay, so deadlock detection with multiple resources of each type becomes a thing. So there are many methods to do that. Okay. Um, so for that one now we have request matrices and allocation matrices. Okay, how many do you need? How many do I have, and etc. Those kind of algorithms exist. Okay, I am skipping them very fast. Okay, and if you detect such things, what would you do? You would preempt. Okay, you would say that okay, I am going to take I am going to take this resource away from you, or I will roll back. I am not going to give you this one, or I will kill one of the processes. Recovery from the deadlock is simple. Okay. So we talked about preemption. It is important we said. Okay, I will skip these parts. Killing and deadlock avoidance. Um, this deadlock avoidance. Remember the third one, the difficult one. It will never let you make a request that will cause the deadlock, most difficult one. Okay, it draws these resource trajectories, and these trajectories are difficult to plot. You need to know a lot about your processes. It's a complicated algorithm to implement, and it is expensive to run actually. So I will skip that one too. And there is a very famous algorithm, Bankier's algorithm, okay, for single resources. Again, to detect the dynamically avoid the deadlocks from being happening. So there is banker's algorithm for single resource and banker's algorithm for multiple resources. Again, these are two algorithms for dynamic deadlock avoidance. Again, I am skipping them. I am just giving you the name. Okay, and we will come to this deadlock prevention. Never let the deadlocks happen. Design your system in a way that, okay, this will never happen again. This will never happen in your system. So you are going to address one of these conditions. If one of them is not satisfied, then deadlocks will not happen, right? Okay, that will not happen. So most people do this. Let's go after the circular wait, attacking circular wait condition. Okay, there is a very simple algorithm. The algorithm is this: always follow the same order for the always follow the same order for the resource assignment to the processes. If you need any of these resources, image setter, printer, plotter, tape drive, and CD-ROM drive, always ask them in this order. Okay, let's say I need printer and tape drive. Okay, first ask for the printer, then the tape drive. Okay, if you need the plotter and CD-ROM, first for the plotter, then the CD-ROM drive. If you do that, okay, if you numerically order all of your resources, and if all of your processes follow this order, then deadlock will never happen. Deadlocks will never happen. Okay, so this is the, as I said before, you are designing your system in a way that, okay, you make it impossible for deadlocks to happen. So if you list all of your resources and give them numbers, and you are going to ask for your um, uh, uh, resources in this order, then you are going to be fine. Deadlocks will never happen. The thing is that you might say that, oh, okay, this is simple enough. Well, I mean, some processes doesn't have to follow these rules. I mean, by coincidence, by accident, by some due to some bug, they may not follow it. That's one. The second thing is that for some systems, the number of resources is so high. It's very large. Okay, and continuously you add dynamically new resources to your system. Okay, making this kind of an ordering may not be possible for some systems. Okay, in that case, this will not work either. Okay, so this is a nice table. Keep this table in mind. Remember, this left side is the condition. All four conditions has to happen for a deadlock to occur. If I prevent any of them, deadlock will not ever occur. Okay, mutual exclusion. Okay, if the process is if the resource is mutually exclusive process, if the resource is mutually exclusive resource, then spooling that resource is a solution. What is spooling? Do you remember spooling? We had the printer spools, right? How does the printer spools work? Nobody has direct access to the printer. You ask the spooler to do something for you, right? So there is a queue. Okay, only the spooler has the printer. You ask the spooler to do something. So that means what? Only the spooler has the printer, and spooler doesn't need any other resources. Unless there is a deadlock with the spooler, there should not be a problem. And there are no deadlocks with the spoolers because the spoolers work on the printers only. So whenever there is a mutually exclusive resource, spool that resource if you can. So with the printers, no problem. Okay. Hold and wait is the second condition, remember. So if you like to prevent hold and wait, you say this: I am going to, whatever I need, whatever I need, okay, I am going to request them at the beginning, okay. If I get them all, I am fine. If I cannot get them all at the same time, I will wait. Okay, so this will prevent hold and wait. Okay, with the no preemption, okay, make it preemptible, and with the circular wait, order resources numerically, and that's going to solve your problems. Okay, so these are the techniques to prevent deadlocks from happening without doing any deadlock detection, without doing any deadlock avoidance. Okay, by structuring your system, your programs this way, you are going to address deadlocks for free, almost for free. I mean, it is free because you are not spending any operating system times or resources to do deadlock detection or avoidance. Okay, I guess that's it. We talked about the live lock and starvation yesterday. That's the end of chapter number 6. Any questions about deadlocks? So what did you learn about the deadlocks? You learn about the deadlocks. They can happen, but they rarely happen. Okay. In order for them to happen, these 4 conditions has to be satisfied. When they happens, your operating system doesn't crash. Okay. Only your processes will not continue. They will suspend. They will be blocked indefinitely. So how would you solve this problem? The most popular technique is just ignore it. Okay. So as operating system experts, designers, you need to know about this. Deadlocks are important. There is a good literature on it, good amount of literature, and a complete chapter about the deadlocks on the operating system books. But at the end of studying all these kind of deadlocks, what you do is just ignoring the problem. It turns out to be the best practical solution. Because in my Linux kernel or Windows kernel, there are many other problems. Okay, every week I am having a crash due to some reason, system crash. Okay, so instead of trying to solve these problems, if I put my effort into preventing deadlocks, that wouldn't be a good strategy, right? That wouldn't be a good strategy. So I don't make that effort, and I just ignore the problem. And if the deadlocks becomes too big problem, maybe use one of these techniques to prevent it from happening or minimize it. Okay, so the algorithms, resource allocation graphs, okay, and resource matrices, allocation matrices, Banker's algorithm, and the projections, resource projections. These are the terminology that you need to remember in your mind. The details of the algorithms, I am not going to talk about them. Okay, if there are no questions, I will start a new chapter. It looks like there are no.
One small, maybe unrelated question. Um, Previously, we have mentioned that there is detection and then there is prevention.
Yeah.
In order to create an operating system that prevents deadlocks, does that require us to write the software as well? Is it like only closed software that, like, or like closed systems as a whole that do this, or can that be achieved by
You are talking about number 3 or number 4?
number 4?
Number 4, the prevention. You design your operating system in a way that you cannot have exclusively access to a resource, such as a printer. Unix is like that, okay? You don't have access to the printer, by yourself as a process. You cannot hold the printer, you cannot request the printer and hold it. You just submit your jobs to the spooler, printer spooler, it prints it. So what did you do? You designed your operating system in a way that the printer will never cause a deadlock. Okay? I am not saying that you could design your operating system that prevents all kinds of deadlocks, but you can do a best effort, and the spooling is a very good idea. It was invented in 1960s, and it has other benefits, and it is good for deadlocks, for preventing deadlocks too. Okay, rest is kind of your program structure. If you are writing parallel programs A, B, C, D, E, F, and there is a possibility of deadlocks happening because of the some of the resources, you numerically order them, and you always ask your processes to request the resources using those numerical orders. Okay, so in this case, this is not operating system structure. This is the programming discipline enforced by yourself within your company, within your software team.
So, in order to make a completely preventive operating system, it requires to have this discipline across not only the operating system but across all the other programs as well.
Yeah, well, I mean, it may in some cases it may involve the operating system plus your application software.
I see. Thank you.
Deadlocks happen with the databases a lot because databases, every record that you are writing to is a resource, right? And writing is a problem because you cannot write to a record while somebody is reading it, okay? Because it's going to create some problems. So they need to deal with the deadlocks, but it's an application, and they have their ways of preventing deadlocks or detecting deadlocks, and etc. And by the way, deadlocks happen, and I mean, I wouldn't call them deadlocks, but in Excel, if a cell refers to another cell, and that cell refers to another one, and at the end you are referring to the beginning of the chain, you have some kind of a loop, right? So everybody is waiting for somebody else to calculate something so that I can put it in my cell. So I think they have some kind of a deadlock detection or the cycle detection algorithm in Excel. Try this in Excel and to see if it works. I mean, try to write formulas that uses the other cells, and that cell depends on the other cell, then that cell depends on the other cell, and at the end the last cell depends on the first cell. That's a problem, right? Because you will never calculate this thing, right? So these kind of problems happen in the applications a lot, but for the operating systems, it is not worth detecting them. It is not worth trying to fix them by running some extra software or putting some software engineers to write code for the operating system, because there are many other problems that you can spend your time on more effectively. Okay, good. Any other questions? Any other questions? Okay, if there are no questions, then I will start the new chapter. New chapter is about virtualization. Virtualization and the cloud. Okay. Nowadays, especially big companies or small enterprises, small companies, a few people working on them, they run more than one operating system. Okay. Usually, the Linux is a very good server operating system. They run their web server on Linux, and if you paid lots of money to Microsoft, you need to run your mail server on Windows. Okay, and you have some customers, and you need to run some OS 10 applications. Okay, and other flavors of Unix maybe may has to be run on your system. So what is your solution? You end up running 4 or 5 different types of operating systems. Sometimes you have a very old application, you need it, and that old application doesn't run on the newer versions of the Windows. Okay, so you have to run Windows NT on your system to run that application. So at the end, what you need is running many operating systems at the same time in your company. Okay, well, if you have the money, you buy lots of computers, you put lots of memory on them. Okay, run one operating system on top of each computer, but it's not cheap. You have to pay lots of money to each computer, and each one consumes lots of electricity, and somebody has to maintain them, right? The maintenance is not cheap. So this is a expensive approach to this problem. One possible solution is to use virtual machine technology. What's the virtual machine technology? Okay, it creates the illusion of multiple virtual machines on the same physical hardware. Okay, if this is your hardware with if this is your physical hardware with your CPU, memory, disks, and everything, okay, you put a layer of software on top of it. Okay, virtualization software. I will call virtualization software. Virtualization software task is to give the illusion of multiple virtual machines on the same physical hardware. So you can run Linux here, like an okay, Windows here, and OS 10 here. So whatever you are running on top of Linux, for example, Emacs, here Outlook, here some other application, okay, each one would think that they are this is running on Linux, and this one thinks that the Linux thinks that it has it has a computer that belongs to it. It can do whatever it wants. So this is definitely cheaper than keeping 3 different computers and running 3 different operating systems on top of each other. Why? Because I need to buy only a single hardware platform. That's definitely cheap. Maybe this machine is a very powerful machine. That's good. This machine itself is expensive, but it might be expensive. Yeah, that's true. But instead of buying 3 machines and maintaining 3 of them, it is cheaper than that. Okay. The other thing is this. You don't need to run Emacs all the time. You run it only from time to time when it is needed. If you don't run Emacs, it is idle, right? If this one is idle, this Linux is idle. If Linux is idle most of the time, this part of the system will not use any hardware resources. So this will idle. While I am running these very actively, this can stay idle. So I am not using my hardware resources for the idle parts of the system. Okay, that's a very good solution. Otherwise, what is the alternative? The alternative is this. Alternative is get these okay, buy separate computers for each of these. So this is my hardware 1, hardware 2, and hardware 3, right? So 3 machines, 3 different machines. If Emacs is not doing anything, this hardware, you are wasting that hardware. You are not using it. This one is sitting idle, and I cannot use it for any other purpose. This is consuming electricity, right? This is consuming electricity. And if I need to run my Outlook very hard, I am just overloading this computer hardware too, while my two other computers are sitting idle. So this is not good. Resource sharing isn't a good solution for this one. Okay, but this one uses that. Okay, so virtual machine monitor here, virtualization system or virtual machine monitor is the layer of software that makes this possible. Sometimes it is called hypervisor. Okay, hypervisor. Remember supervisors? Supervisor is part of the operating system that manages your processes. Okay, in your operating system there is a supervisor. That supervisor manages your um, processes. Hypervisor is doing the same thing one level up, right? Hypervisor is managing your operating systems. You may think it that way. So VMM is also known as a hypervisor. Okay, and there are many types of hypervisors, but usually we like to categorize them into two groups: type 1 hypervisors and type 2 hypervisors. Okay, whatever the type of hypervisors are, okay, the thing is this: either way, virtualization allows a single computer to host multiple virtual machines, each potentially running a completely different operating system. Nobody knows about each operating system doesn't know anything about the other operating system. They don't know that they are working on a virtual machine, but at the end, the final product is the same as the original operating system running on separate hardware. Okay, so let's look at this type 1 and type 2 hypervisors. Type 1 hypervisor, okay, it runs on the bare metal. That means that it runs on the hardware itself. This is type 1 hypervisor virtualization system. Okay, it runs on the bare metal. And type 2 hypervisor doesn't work that way. It does this. Okay, maybe this is a good example. Should I erase all the stuff that I had from last year? Yeah, I can. I think I'm going to do that. I don't need it because I'm not going to go fast on this one. So what happened? Clear, clear. Maybe it cleared it. Yeah, I think it's gone. Okay, good. Okay, so this is type 1 hypervisor. It runs directly on top of hardware. Okay, and its task is to show the upper layer softwares. Okay, software like they have their own hardware. Okay, this Windows system thinks that it is running on the bare hardware, but it is not. This is called type 1 hypervisor. Type 2 hypervisor is a little bit different. Type 2 hypervisor works on top of a host operating system. There is an operating system running on it. So this type 2 hypervisor is running as an application program actually. The task of this application program is to show itself as a uh, bare hardware to the guest operating system. Okay, for example, Windows here. Of course, there are other. Of course, there are other host operating system processes already available. For your homework, you are using this structure, right? The virtual machine, the VMware machine. We are giving you a VMware machine, right? VMware. The
Yes, we have.
mhm. So your type 2 hypervisor is VMware. On top of it, you are running Linux. Okay. And on top of that, you have your own applications, your own compiler, your own editor, etc. Whatever program you compiled with. Okay, good.
So a type 1 hypervisor is what we would find in data centers or servers where they have multiple different machines running, right?
It is possible to have multiple operating systems running on the type 2 hypervisor too. I mean, type 1 hypervisor, I mean, if you mean that type of hypervisor is more complicated and it is used by large corporations, that's not true, no. I mean, they have advantages and disadvantages. Okay.
Okay.
Which one is more complicated, do you think? Which one is more complicated to implement?
Type 1.
Do you think so? Why?
I do.
No, I think two is more complicated.
2 is more complicated
Because
actually.
there are no layers.
Yeah, because with the 2, you need to know a lot about the host operating system. And on top of it, you are, okay, trying to provide all kind of things that this type 1 hypervisor provides. Okay?
But I think type 1 is more complicated because it is maybe hardware specific more than type 2 is.
Okay, let's think about what this one does. Okay? If Windows is okay, let's look at this system. This type 1 hypervisor is using this hardware, right? So it's a piece of software. If we look at this, okay, let me draw some small picture here. This is my hardware, typical picture that I had drawn at the beginning of the semester. This is your operating systems and these are your applications, right? A1, A2, A3. So which part of the software stack is running in kernel mode? Okay, this is kernel, right? And this is user space. Operating system is running in the kernel mode, kernel space. Let's try to see the picture here. What part of this software stack is running in the kernel mode? Is Windows here? Let me draw this line and draw this line. Okay. Is Windows running in the kernel mode? Is Linux running in the kernel mode? How about Type 1 hypervisor? Is Type 1 hypervisor running in the kernel mode?
I think the type 1 hypervisor is the kernel mode and the Windows and the Linux ones are not.
So this is in the kernel mode. Windows and Linux, they are running in the user mode. Very weird. Very weird. So how come the Windows can have access to the, for example, page table, for example, the IO port space? For Windows to run it, right, it needs to access to the page table. It needs access to the IO port addresses. That's what the operating systems do, right? So what's going to happen? What's going to happen? I mean, I am trying to see what this Type 1 hypervisor does. If this, so Type 1 hypervisor is a very simple scheduler. It's a very simple scheduler in this case, right? It's a very simple scheduler. Whenever it gets a trap, it just handles it. That's what it does. If this Windows application, I mean, I'm talking about Windows like an application, right? Okay, because for me it's running in the user space now. If that Windows application is running regular instructions, then Type 1 hypervisor doesn't do anything at all. Type 1 hypervisor doesn't do anything at all. The same with the Linux. Okay, Type 1 hypervisor doesn't do anything. It just lets them use those regular instructions and they will do. Okay, but if Windows runs a privileged instruction, since it is in the user mode, what's going to happen? That's going to cause a trap to the kernel. In that case, Type 1 hypervisor gets it. For example, Windows is trying to access the IO port space, and Type 1 hypervisor regulates it. It says that okay, this part of the disk belongs to Windows, then it can do it. or it will do the necessary translations, and it will kind of translate the whatever requested by Windows to the hardware terms, and it will let it run, and after that it will say that okay, I am done, I'm back to you Windows. Okay, and it will do the same thing for the Linux. So all it does is it just translates those privileged instructions in a safe and efficient way to the hardware language. It is not that much actually. I mean, it doesn't know anything about operating system. It doesn't know about complications of the memory management. It doesn't know much about stuff, and most of the time, it uses whatever available from the Windows and Linux systems. Okay, Type 2 is kind of different because this one has to translate all these kind of requests to the host operating system calls. Okay, and again, this is running in kernel mode. This is running in user mode. Okay, this is running in user mode. So it is a little bit weird. Why? Because I mean, you are running an operating system in the user mode, yet you are letting your operating system and the user mode operating system to use privileged instructions. So who is responsible for the translations? This type 1 hypervisor or type 2 hypervisor. So type 2 hypervisor is a little bit more complicated because it lives between these two operating systems. Okay, if the guest operating system Windows is running regular, okay, if this one is running uh, regular instructions, then this one let it go, and it will run on the hardware. Of course, these are not done dynamically. Okay, while this one is using the CPU, nobody intervenes with it. It just uses the CPU. It will use the memory. If they are doing something privileged, then the hardware traps it to the kernel. Okay.
So what I understood is that type 2 is just translating it from one operating system language to another, whereas
Yeah.
the type 1 is just queuing up the requests that come from different operating systems or scheduling between them.
Yes. Typefan is less complicated than to write. I mean, maybe it's not a very good idea to compare them in terms of their complexities, but don't think that Type 1 is more powerful than Type 2, or it is used by the large corporation. That's what you ask. That's what I'm saying.
Yes, yes.
Okay, good. So I like to talk about these virtual operating systems because understanding the virtual operating systems will make you understand the operating systems much better, because you can realize that our operating system is doing this and this and this task and etc. Okay, so talking about the virtualization of the operating system is a good idea. But it looks like I am out of time for the first part of the lecture. Let me take 10 minutes of break. Okay, after the break we will come back and we will finish up with the course for this semester. Okay, 10 minutes of break. Let's be here at 12:35. Arkadaş almış mı? O yok ortak odası. He? Perşembe günü akşam zaten yaptık. Ne? Ne diyor? Yetiştirebilir misin sen? Yetiştiririm. Ben cuma günü akşam aldım ya. Şeyden dolayı, ben yeni ertesi gün yatıracak büyük ihtimalle. Cumartesi pazar yatacak. Niye yatıyoruz? Yön tek aldım. Ben de bir tek aldım. Ben cuma günü yatacağım. Biliyor musun? İstediğine dokunmadım. Yok ben dersteyim. Ben böyle çıkabilir miyim? Ben de yazmadım mesela, ben yazdım bize. Belki de yazmadım. Tam değiştirebilirsin yani, onu şey yapabilirsin. Öbürsünü senden alırım orada öbürsünü. Ben getirdim mi? Bir tane de onu benim odaya koyardım ya. Şöyle yaptık çalışma tahmin ediyorum da bu Buran görüyor musun? Hocam dersim var ya. Ha, dersin? Bu saatte maalesef şu arkadaşın yüzünden.
Yani zaten parmağın çatlak olmazsa rekor kırardın herhalde. Hadi hadi. Çok çok sevindim Burak. Yine inşallah şimdi ya. Sınavda geçtiniz tamam.
Ya benim öğlen saatinde şeyim var da toplantıları falan. Sadece perşembe saat şey onu bir tane şey yap. 17'ye ben 17'ye geçtim. 17 10 11. Okay, so that's the difference between type 1 and type 2 hypervisors. Um, One concern about these kind of virtual systems, hypervisors, is that they say that what happens if type 1 hypervisor has a bug, okay? If this type 1 hypervisor crashes, everything crashes, right? So maybe it's not a good idea. Maybe it's not a good idea to put all of your email servers, web servers, security servers, and etc. on the same piece of software. Okay, that's one of the concerns. You are doing something for cheap, but this is not as reliable. But the idea is this. Okay, the idea is this. Okay, uh, most service outages. Okay, of course the other one is the hardware. If this hardware fails, everything is going to go down. So the thing is that the statistics tell us that most service outages are not because of the hardware failures, okay, but they are because of the ill-designed, unreliable, and buggy and poorly configured software and operating systems. They are all software problems, okay. With virtual machines, okay, the virtual machines are again piece of software, but they have the smallest amount of code. I mean, this type 1 hypervisor here is very small piece of code compared to this Windows or Linux. Okay, so that means what? Only a very small amount of code runs in the privileged kernel mode. The rest of them runs in the user mode. Okay, if this Windows does something bad, only this Windows is going to crash, and it is very likely that it's going to do something bad. Okay, it's going to crash. The rest of the system will keep running because it is very unlikely that you will have a bug in this hypervisor than a bug in Windows or Linux, because Windows and Linux, they have a much larger kernels, and now I have running those kernels in the user mode, not in the kernel mode. So this is kind of an advantage. This is kind of an advantage. Okay, so a hypervisor is way simpler than a complete operating system, and only the hypervisor runs in the, especially type 1 hypervisors, runs in the privilege mode. So this is the best of both worlds. Okay, best of both worlds. So reliability of virtualization is not a very big issue. Of course, if it comes to hardware, if there is a power failure, power supply failure with the hardware, then we are not in a good situation. But um, the chance of having that is small, and chance of having that is small, and probably, by the way, I mean, remember the alternative way of doing stuff. Where is my nice picture that I had drawn? Where is it? Where did I put my pictures? Come on. Remember, I had drawn a picture somewhere. Did I erase it? Oh yeah, because I had. Okay, I deleted it. Okay, so instead of running a simple single hardware, I can run two computers, one for Windows and one for Linux. Okay, if the expected lifetime for hardware is 5,000 hours, if you are running two of them at the same time, okay, you are not going to get 5,000 hours from both of them. Okay, so if there is a 1 in a million chance that your hardware is going to fail for a given single day, if you are running two of them, okay, you have 2 in a million chance that you are going to one of the servers are going to fail, right? So you are increasing your chance of having a failure with the hardware if you run more than one hardware platform. So running it this way is better. Running it this way is better in terms of having hardware problems too. Okay, so advantages, of course. Advantages are um, we save on hardware, electricity, and rack space. These are all important. Okay, and another one is um, uh, moving your stuff from one platform to another platform is so easy. Okay, let's say I have three large computers, one, two, three, and top of them I am running Typefan hypervisor, Typefan hypervisor, and Typefan hypervisor. Okay. On this first machine, I have Windows and Linux. On this one, OS X, okay, OS 10, Unix and Windows, Linux and Mac operating system. Now I decided that maybe I should move this Windows from this location to that location because I need to balance some load. It is easy to do now. Why? Because this Windows is not dependent on this hardware. All it depends on this type 1 hypervisor. And this could be done automatically by software without any manual interruptions. Okay? So migrating virtual machines is much easier than migrating processes running on normal operating system. Okay? So for load balancing across multiple servers. So this is much better. Also, virtual machines for software development. This is what we do actually. This is what we are doing with the for your homeworks. We are using virtual machines for software developments instead of instead of uh, instead of installing Linux on your computer. Even if you have Linux on your computer, I like you to use my exact Linux configuration on your system. How am I going to do that? Of course, using a virtual machine is a good idea because that virtual machine has specific configuration, and I know what that configuration is. And whatever you run on that configuration, it should produce exactly the same thing on my mind. Okay. And cloud computing is an example of virtualization, but we will not talk about that cloud computing for now. Okay, so these are the advantages. I think we are convinced that virtualization is a good idea. And let's look at requirements for the virtualization right now. Okay, so if I am going to virtualize something, what kind of things should I be careful about? Okay, three things: safety, fidelity, and efficiency. What is safety? Safety is the hypervisor should have the full control of virtualized resources. Okay, by running this hypervisor, you shouldn't expose you shouldn't expose loopholes to the upper level software. An hypervisor should have the full control of virtualized resources. There should not be any power holes, security holes with your hypervisor. That's one thing. The second thing is fidelity. Okay, what are we saying all the time? We say that if this Windows operating system is running on top of hypervisor, type 1 hypervisor, okay, this Windows system should should 100% feel that it is running on bare hardware. Okay, so the program behavior should be exactly the same. It should be the identical. It should not behave differently because it is running on hypervisor. And of course, the third one may be the most important one in terms of practicality. It should be efficient. Why we are saying that? Because if if I am running a Type 1 hypervisor and this Windows becomes 2 times, 4 times slower than the original, nobody is going to use it. Okay, all the advantages will go away. Your web service will be slow. Nobody would want you, which want would use your email service on the virtual platforms and etc. So it should be efficient, and we are going to talk about this efficiency a lot. And there will be some surprises about the efficiency, if we have hardware help or no hardware help, and etc. Okay, so uh, safety, fidelity, and efficiency are the three things. Unfortunately, there will be issues with the efficiency sometimes, and I'm sure you are realizing it, but it is tolerable. Fidelity sometimes doesn't work. For example, your specialized your specialized graphics card may not work with the virtual machines, or some of the specialized hardware, I/O hardware, will not work. And this systems virtualization systems might introduce some safety problems. And as I said, we will not be 100% on any of these three dimensions, but what do we say? We should score well. We don't say score full. We should say, we are saying score well in three dimensions. Okay, good. So let's look at the virtualization techniques a little bit. Let's try to understand what's going on when we do the virtualization. Okay, let's say I am doing this. Again, hardware, Typefan, hypervisor, OS, and application. Okay, consider each instruction, okay, in an interpreter and perform exactly what is needed for that instruction. We are using this interpreter technique, okay, interpreter technique. This operating system is trying to execute an instruction, and let's say this Typefan hypervisor takes that instruction. Every time you run something, that Typefan hypervisor is executing that instruction in an interpretive way. Okay, it looks inefficient, but let's say we are doing it that way. Okay, but then we realize that if I am incrementing a register, okay, I mean this application or operating system is trying to increment a register. Okay, they can do it. That's not a privileged instruction. They can do it. For that case, I don't have to do any interpretation. I just let it run on the hardware. Okay. So for those kind of instructions, I don't have to do any interpretation. It can all run on the hardware. So there is no efficiency loss here. Okay. Those kind of instructions are those kind of instructions are uh, free to use the hardware, and they are as efficient as the original. Okay, uh, but instructions that needs the kernel privileges, of course, they cannot run on the bare hardware. Okay, if this operating system here, Windows operating system, needs to modify the page table, virtual page table, then that's a specialized instruction. This hypervisor cannot let that instruction run on the hardware. So what do we do? This Typefan hypervisor here interprets that instruction. It changes that instruction. It changes the page table, but it changes the page table in a way that it doesn't interfere with the other operating systems. Okay, this is OS2. Okay, because this hardware has only one page table. The task of Typefan hypervisor is to show to each operating system that they have their own page tables. So if the OS1 tries to change the page table, this Typefan hypervisor cannot let it happen directly. It has to make some changes, it has to do some modifications. That's the interpretation part. Okay, So that's one virtualization technique, interpreting, okay, many instructions at this level. If the number of instructions that you are interpreting, instead of letting them run directly on the hardware, is too many, then that means that you are going to be inefficient. Because this is a piece of software, remember? This is a piece of software, and it has to run on the CPU. It has to use the computer resources. So I cannot let this hypervisor use too much CPU time. Okay, so let's look at some classification of the uh, virtualization packages, and these are some of the very well known hypervisor types. Okay, we are using VMware, and there are other types of virtualization stuff. Let's look at this column first, virtualization method. Okay, um, virtualization without hardware support, and we are going to talk about what we mean by hardware support. There is a technique called para virtualization, and we are going to talk about in a few minutes, and virtualization with hardware support and the process virtualization. Okay, um, the ones that we are using, the ones that you are using falls in this category. Okay, the one that you are using is a type 2 hypervisor, and we use the hardware support. Okay, uh, what is hardware support? Hardware support is this. Do I have a yeah, I have a slide about that. Okay, if the guest operating system, okay, tries to execute an instruction that needs the privilege mode, because that guest operating system, draw it again, hardware, this is hypervisor, and this is the operating system. Okay, operating system, but it's a guest operating system. Okay, if the guest operating system is trying to by the way, okay, let me put some application on it. This is application. Remember, this one is in the kernel mode, this one is in the user mode. If this guest operating system tries to execute a privilege instruction, well, this guest operating system doesn't know that it runs on this hypervisor. It thinks that it is running on hardware. It thinks that it is in the kernel mode. This guest operating system is trying to run a privilege instruction. Okay, so what would happen if you run the privilege instruction in the user mode? Tell me the behavior. Okay, as a regular programmer, you write a program. Your program is trying to access the page table. What happens?
You get shut down.
You get shut down by the operating system, right? The operating system says that this program is trying to execute an illegal instruction. That's what happens. Okay, so the hardware tells the kernel mode. Okay, the hardware traps to the kernel, and it says that somebody is trying to execute a privileged instruction. Okay, but if you have virtualization support by the hardware, this trap happens in a specific way. This trap happens to the hypervisor again. This trap happens to the hypervisor, and the hypervisor knows what kind of instruction being executed, and the hypervisor takes care of it. Hypervisor knows that this request comes from the guest operating system. By the way, guest operating system is running like a regular process now. Hypervisor knows what process it is. It says that it is coming from the guest operating system, and it's a privilege instruction. I am going to reinterpret it. Okay, if you have the virtualization support, Intel platforms, Intel CPUs did not support virtualization, I think until 2010s or 2005 maybe. Okay, they did not support the virtualization. So if the guest operating system tries to execute such a such a if it tries to execute such a privileged instruction, then the guest operating system simply crashes. That's it. Or sometimes that instruction is ignored. It is just ignored. That's it. If you try to modify the page table as a regular process, the Intel platform just ignores your instruction. So that makes it impossible to get hardware help if you are doing the virtualization. That doesn't mean that you cannot do the virtualization on such platforms. It was still possible. And these kind of hypervisors, VMware Workstation 1, okay, used that technique. They didn't get any help from the CPU, okay. All they did was, okay, they when they get a new program, okay, operating system, okay, they analyze the operating system or the processes on the fly. They detect the privileged instructions. They change those privileged instructions with their own system calls, and they modify the programs on the fly, and they let them run that way. Okay, so previously they had these kind of hypervisors, and they weren't that slow. Okay, and they were successful, and they sometimes they were as fast as the original program. Okay, so hardware help doesn't mean that that's the only way. You could do the virtualization without the hardware support. So if in this case this one has piece of code, okay, this is instruction 1, instruction 2, instruction 3, and this instruction 4 is a, let's say this is the privileged one. These are all regular instructions. So this hypervisor analyzes this code, and it says that this instruction 4 is going to create a problem for me. So I am going to replace it with something else. That something else is a special instruction set that will handle this privileged instruction in this layer of code. The rest of them will run on the bare hardware, but this one will be replaced. So it's kind of a more pain, so more chance of getting a crash out of your hypervisors, but it is still possible. It was still possible. Okay. So I told you that I am going to look at this para virtualization in a few minutes, and then I have this the fourth one, the process virtualization. You heard about Wine, okay? Wine is um, Wine is API implementation of Windows on Linux. API implementation of Windows on Linux. Just a minute. Şeyler bunlar değil mi? Burayı paraflamıyor muyuz?
Paraflamışlar ama.
Bunda belki bir şey. Teşekkürler. So, one is API implementation of Windows. Remember Windows.h? Okay, Windows.h is the interface of Windows operating system. Any program that is supposed to run on Windows needs to use the Windows.h, right? If you implement all the Windows.h functions, everything, then that means that your programs can compile and run on anywhere that this wine is available. So that's called the process virtualization. That used to be very big effort on it, but nowadays I think it kind of died off. I don't know what's the latest news about wine. Our
Why?
our type 2
Strong.
hypervisors are so efficient and so popular, that we don't use those kind of approaches anymore. Did somebody say something?
I said that wine is still very powerful and still heavily used, especially with people who try to game on Linux, because a lot of virtual machines are extremely well, they are not as responsive for video games as running it on native. So Wine and there is also Proton. They are very powerful with the gaming community.
Okay, yeah, I didn't know that. It has been a while. I mean, once we get hardware help, and once we had products on this box here, I stopped looking at wine because that was, I mean, responsiveness or efficiency. I don't care much because I mean, why would I use Windows on my Linux machine? Because of Office, maybe some applications, maybe, and I don't need them to be very very fast because our machines are already fast. But for the games like that kind of stuff, of course you may need them. Yeah, that's different. Okay, so that's called the process virtualization. Wine is an example of it. And let's look at this para virtualization stuff. Okay, para virtualization is kind of hypervisor, but it is not a perfect hypervisor. It kind of makes a trade-off. It kind of makes a compromise. Remember, we said that there are three things about the virtualization: safety, fidelity, and efficiency. Okay, fidelity. Let's get rid of this fidelity thing. Not 100%, but some of it. What happens if the guest operating system knows that it is running on a hypervisor? Okay, that's called para virtualization. So I have this modified Linux. Okay, that modified Linux knows that it is running on a hypervisor, maybe possibly a microkernel. Remember the microkernels? They are operating systems, but they are very very small. Okay, so you are running this microkernel on top of hardware, and this modified Linux knows that it is running on this microkernel. Whenever it needs privileged functionality, it makes a system call to the microkernel, trapped due to the hypervisor call. Okay, so modified Linux is doing that. That's called the para virtualization. So what is the advantage? The advantage is the whole picture. I mean, the combined picture of these two becomes simple here because you can take advantage of the whole picture. It knows about anything. But disadvantages that you have to modify your operating system. And although, of course, I have the source code for the Linux, I can modify it the way I want. I don't have the source code for Windows for the latest versions. I don't have the source code for the Macintosh operating system. Okay, Mac operating system. So para virtualization, I think we will come back to this later. Is a way of doing this. It is in between para virtualization, and there is a example for it, Zen 1.0. I think there are newer versions of it, of course. Okay, so it never aims to prevent the virtual machine. That looks like so. Fidelity is not there. I mean, the second one, remember, safety, fidelity, and the efficiency. Of course, safety of course, efficiency, but fidelity, no, because that machine know that it is running on some kind of a virtual platform. It offers a set of hypercalls, okay, and the guest knows which hypercalls there are, and it uses those hypercalls to do whatever it needs, okay, and guest use those hypercalls to do the privileged operations, okay. Then the overall system, and we are not talking about the hypervisor part or the operating system, but the overall system is simpler and most of the time faster, because you can take advantage of the current configuration, okay. That's the idea of para virtualization. Tamam. Okay, I am reading this message here, and I am reading it. I am saying tamam to you. That's okay. That's what's happening. So, techniques for efficient virtualization. Again, I think we talked about this a little bit. Yeah, because I talked about this virtualization support. That's what happens. Okay, virtual user mode, virtual kernel mode, and this is the real kernel mode. When this operating system causes runs a privileged instruction, it traps to the Typefan hypervisor, and that's because of the hardware hub. Hardware does that, okay. Hardware says that if somebody runs this one on the user mode, okay, it might be either because of an error, somebody is trying to hack the system, or this guy is running a virtual system. So it lets the kernel mode software know that such and such is happening. Instruction being run is this, parameters are that. What are you going to do? It is up to the hypervisor to execute it the way it wants. Regularly, if this is the regular picture, if this one tries to update the page table in the virtual user mode, okay, question for you. When I execute a privileged instruction here, there is a trap to the hypervisor, right? How about this one? If I try to run a privileged instruction in the user mode, in the virtual user mode, what happens?
Doesn't the guest operating system decline it from the get-go?
What do you mean by operating system?
The guest operating system, the
No,
one
no.
is running the virtual kernel mode.
Well, this picture is not a very good picture, actually. The picture is something like this. The real picture is something like this. This is my hardware. This is my type 1 hypervisor. This is my operating system, and these are my processes. That's the picture, actually. This operating system, of course, type 1 hypervisor knows it. This is the operating system. Whenever this one causes a privileged instruction, this type 1 hypervisor tries to help this operating system to execute it. But if one of these tries to execute a privileged instruction, again, this type 1 hypervisor gets it, and it does whatever is necessary. It says that, okay, you are a regular application, you don't have permission to run this instruction, so I am going to shut you down. Okay, I am going to shut you down. If this one says that open a file for me, a system call, okay, system call is received by the type 1 hypervisor. Type 1 hypervisor cannot, of course, handle it. Who is going to handle it? The operating system. It lets the operating system handle that kind of call. Okay, so the hardware is not sophisticated enough to know that. But there are those kind of hardware. Remember the rings of the Multics operating system? Ring 0, ring 1, ring 2, and ring 3. So if we had the ring structure, then this would be 0, 1, 2, 3, it goes that way. But not all the CPUs support this kind of ring structure. So you either have the kernel mode or the user mode. Okay. If this one makes a system call, this one receives it, and it lets the guest operating system handle it. Okay. If this one executes the bad privilege instruction, the hypervisor is say that, okay, you are not marked as an operating system. I'm going to shut you down. Okay.
Now, why are the processes running independently of the operating system?
You mean this picture?
Yes.
That's the only way, because the type 1 hypervisor is a scheduler, right? It schedules these processes. An operating system is another process, and it has to use the CPU. And actually, on our machines we are doing the same thing too. Okay, they all are processes. Only the operating system runs in the privileged mode. The rest of them runs in the user mode. Okay, and the reason why we are showing it this way is that if this user process makes a system call, okay, that system call is received by the operating system because it makes a trap, hardware trap. But in this case, hardware traps are received by the hypervisor, not by the guest operating system. Because when you make a trap system call, you go into the kernel mode, right? And the kernel mode is the hypervisor, not the guest operating system.
So the way that I imagined it is that the hypervisor is like an operating system for operating systems, or a scheduler for operating
That's
systems.
why it is called hypervisor. It is not supervisor. There is a supervisor inside the operating system that schedules between the operating system processes. Okay, and the hypervisor is a hypervisor because it schedules between the operating systems and their processes and the other operating systems.
Okay, nice.
That's why it is called hypervisor. Remember, super speed, hyper speed. Okay, super scalar, hyper scalar. Hyper is like one level up of super, right? Is there a Hyperman? Is there a character called Hyperman? There is a Superman. I wonder if there is a Hyperman.
No, I don't think so,
I
sir.
haven't heard of him, but you can pitch that for Marvel or for DC, you know.
Well, I think that somebody had that idea, but maybe it didn't fly. Okay, I'm not interested. And whatever it is, I mean, you can always virtualize a Superman in the hyper character okay, whatever. Okay, I skipped that part. Virtualization support again on CPUs with virtualization support, such as our Intel chips of the last 15 years, maybe yeah, 15 years. We have the virtualization support. When the guest operating system executes a sensitive instruction, a trap to the hypervisor does occur. Previously, this kind of stuff that just it was ignored, and virtualization was difficult. So what that didn't stop people from doing those kind of virtualization. So virtualizing the unvirtualizable. So we are talking about this box here. We are talking about this box or this box. Virtualization without hardware support. So virtualizing the unvirtualizable. Maybe I should put them in quotes because of course it's virtualizable. So you use the clever use of binary translation. So you are on the fly translating your code, binary code, so that your special instructions from the guest operating system is taken away and it is replaced with something else. Okay, this kind of hypervisor makes sure that no sensitive instructions in the guest kernel code. Okay, the guest kernel code, guest operating system, draw the same thing again for the 15th time. Hardware hypervisor, okay, type 1 hypervisor, and this is the guest operating system. Okay, the hypervisor here makes sure that no sensitive instruction in the guest kernel code. The guest kernel code, while it is running, okay, it is translated. If there is a special instruction, okay, it is special instruction, it rewrites the code. It rewrites the code. It says that you are not going to execute that code, but you are going to execute that code. So it looks so expensive, right? It looks so expensive because while you are executing it, you are translating it. It's like running Java. Why Java is slower than C++, 2 times, 3 times slower? Because there is JVM in between, right? You have to run JVM too, okay? But sometimes if you are smart, okay, if you write your Java code very carefully, your code, especially if you develop it very fast, your code could be as fast as C code if you take advantage of the Java libraries. Okay, so that's what they are doing actually. So they come up with this idea of basic block. Basic block is a short straight line sequence of instructions that ends with a branch. So inside the basic block, there is nothing special. Okay, when you let the hardware run it, it just runs, and usually they mark these basic blocks and they let them run on the bare hardware until there is a branch. Why do they stop when there is a branch? Because when there is a branch, that means that your pipeline structure will be inefficient. At that point, maybe I can say that this is the end of the block. I can translate this block, or I can just let this block run. When it is time to branch, I am going to get hit by the branching costs of the pipelining anyway. So it does these translations block by block, and it keeps those blocks cached in some place. Okay, when I run that code again, I don't do this translation again. Okay, so this is dynamic translation and emulation. So basic blocks are not translated at all. They run on the hardware. When there is a special instruction, then I have to run some emulation. Okay, it sounds expensive, but typically it is not. And surprisingly, translated blocks are cached. Okay, so no translation is needed in the future. And sometimes, where is that? There was a very nice sentence. Okay, sometimes these translated code is surprising. Sometimes these translated code may be more efficient than the original code. How could that happen? I mean, this guest operating system, there is this OS, and now I have this hardware. There's no OS, it is application one, and this operating system, same operating system, and application one. Sometimes this application one runs faster on this configuration than this one. How could that happen with this kind of uh, dynamic translation and emulation? How could that happen? Maybe instead of doing this, maybe I should draw it like a type 2 hypervisor. Okay, this is my host OS, and this is my type 2 hypervisor, and this is my OS, this is my A1. Sometimes this A1 is faster than this A1. How could this happen? There is this host OS and this hypervisor. Remember this. This is in kernel mode. This is in kernel mode. Okay, this is in user mode. This is in user mode. So this type 2 hypervisor here runs in the user mode. Whatever emulation you are doing, it is in the user mode. There is no trap to the kernel. So there is no context switching sometimes. Okay? If you save the context switching to the kernel, sometimes you end up A1 being faster on this kind of hypervisors. So the operating system world is a weird place if you take these kind of advantages. Okay? So sometimes you end up having dynamic translation emulation being faster than the original. I'm not saying that it's going to happen all the time, but sometimes it happens. Sometimes it happens. Okay, good. I think that's it for today. I was I was planning to stop here and not talk much about the rest of the virtualization, but I don't know why, but I think I will continue. I will do one more class on Monday, okay? And I will give you more information about this virtualization, how we virtualize the memory, how we virtualize the CPU, and how our popular, okay, VMware stuff, VMware Type 1 hypervisor, Type 2 hypervisors work. I will try to give you some more examples, and I expect you to read about this whole chapter later in the summer. Okay, that's it for today. And today is not the last lecture of the semester. On Monday, I will do one extra lecture. Okay. So, what is the due date for your homework? Is it today, tomorrow,
I think Thursday.
Thursday, on third?
Yeah,
Okay.
Thursday
Then
night.
your new homework should be ready by then. Your last homework will be implementation of file system, or
Uh,
or
Sir,
maybe a.
is the final date? Is the final date clear? Final exam date?
Well, just a minute. It is, I think it is, I am, maybe I shouldn't, okay. This is just to give you an idea. This is not definite date. Uh, Yesterday we received an email from the TA. I think it is Monday, second week of finals period. Let me see. No, still loading. Yeah, okay. So finals undergrad is 21st between 9:30 and 12:30. June 21st. As I said, this is not final dates. I mean, this is not the definite dates. They may change. I don't know. But soon they will be available for you. Okay? 21st, Monday. Is 21st Monday?
Correct.
Yeah, okay. In the morning.
On the class lecture, half dersi tatili mi olur hocam?
Well, I don't. You mean are we going to do it online or on site? Is that what you mean?
Yes.
I think it's going to be online, unfortunately.
Sir, is the fourth homework connected to the second homework or is
No,
it
no, no, no.
completely
It will be
separate?
completely independent.
Okay, thank you.
Okay. Okay. I'll see you on Monday then.
Have a nice day,
Sir,
sir.
we have a midterm grades can be announcements.
Yeah, sure. Yeah. As soon as I read them, I will announce them. Yeah. I started. I started thinking about it. I started thinking about reading your midterms. Yeah, that's a good idea. I will read them. I think I will read the first. I started actually reading the first one. I kind of the first question. So this is what I'm going to do. I will read them question by question, and I will email you like I did last semester. I will email you the results for each question.
Thank you.
Okay. Okay. Bye now.
Have a nice day, sir.
Thank you.
Have a
You
nice
too.
day.
Bye.